The F statistic is a ratio of the average variability between groups to the average variability within groups. So the mean variability between groups divided by the mean variability within each group. So if there's really a difference between the groups, then we would expect the F statistic to be which of these? Higher than we would observe by random chance or lower than we would observe by random chance? We would expect it to be higher. So remember, we want the difference between the groups, to be a lot bigger than the spread within each group. So we'd be looking for an F statistic that's pretty large. And remember, the numerator of the F statistic is the between group, so how far apart are the means, and the denominator is the within the group, so how spread out is each individual group. So if there's a difference, we would expect that the between group variability will be higher. So if the null hypothesis is true, what kind of F statistic would we observe just by random chance? And let's go back here and just see what our, I think it's down here, our F statistic for this problem is. Yep, okay. So let's talk about this. The F distribution, so this is a new distribution for us. If the following conditions hold, sample sizes have to be large. So just as before with means, we need every sample size to be at least 30, or you have to be able to know or assume that your data is relatively normally distributed. We need the variability to be similar in all the groups. So as a rule of thumb, this is violated if the standard deviation of any of the groups is more than double the standard deviation of any of the other groups. So if that happens, then we would say variability is not similar and we can't use this. And again, we're assuming the null hypothesis is true. So the F statistic follows an F distribution. It has 2 degrees of freedom. One for the numerator, which will be number of groups minus 1, and one for the denominator, which will be the total sample size minus that number of groups, k. And now for F statistics, the p-value is always in the upper tail. So it's just like our chi-square, it's always right-tailed. So for our cuckoo bird eggs, the equal variability condition is satisfied, but the sample sizes are actually small, so we can only use the F distribution if the data is normal. Because see, here are all the individual sample sizes. Oh, do we not have it up here? Here we go. So the sample sizes, notice that a couple of them, most of them are less than 30. Okay, so we've already, because you won't need to compute the F statistic by hand, we have already computed the F statistic for you. And the F statistic is this 10.190. That, by the way, is our test statistics. So the same idea as with all of our hypothesis testing, that we would have an F statistic. Notice here, this is the degrees of freedom for the numerator, degrees of freedom for the denominator. This is our k minus 1, and this is our n minus k. Because the total sample size back here was 120. And if our number of groups is 5, then it's going to be 120 minus 5, and that's how you see we are getting degrees of freedom of 115. So now we're going to use our graphing calculator to find the p-value for our F statistic. If you look on your graphing calculator in the distributions menu, you will see that at number 9, you see FPDF, but keep going, and at 0, you will see FCDF, and that's the choice that we need. Notice it has lower bound, upper bound, degrees of freedom of the numerator, degrees of freedom of the denominator. So we will be doing FCDF. The lower bound will be 10.190. It's always right-tailed, so the upper bound will always be E99. And then it's the degrees of freedom of the numerator. So for this problem, that's 4. And then degrees of freedom of the denominator. So for this problem, that's 115. So that's what we're going to put into the calculator. 10.190 190. Upper bound is E99. Degrees of freedom of our numerator is 4. Degrees of freedom of the denominator is 115. And we're getting 4.258921236 e to the negative 7. So remember, that's scientific notation, so that means I'm actually moving the decimals 7 places to the left. So this would be 1, 2, 3, 4, 5, 6, 4, 2, 5, 8, 9, 2, 1, 2, 3, 6, which if we round to 3 decimals as we usually do, will be 0.000. And that is our p-value. Now with a p-value, oops, we should have actually put all this up here. With a p-value this small, what would our generic conclusion be, and what would our conclusion in context be? I do also want to point out that this is from StatKey, and you'll see that when you did the p-value for 10.190 and to the right, you got 4.3 e to the negative 7, which is exactly close to what we had here. Now, let's do our generic conclusion, our conclusion in context. Now, with a p-value of 0, that's much smaller than any alpha level. So our generic conclusion would be to reject the null. And then our conclusion in context would be that we have evidence that the population means are not all the same. And what do we mean by that? What we mean is that the cuckoo, oops, spelled that wrong, cuckoo birds eggs, cuckoo birds eggs found in the nests of different species differ in size. That's what we were testing. Okay, so let's summarize what ANOVA is for and what it's about. So analysis of variance is used to test for a difference in means between groups by comparing the variability between groups to the variability within groups. Now, the sum of squares is what we use to measure the variability. The F statistic is the ratio of average variability between groups to the average variability within groups. And the F statistic follows an F distribution. Again, we've got a size requirement for that. So only if my sample sizes are large or the data is normal. The variability, another requirement is that the variability is equal across the groups and the null hypothesis is true. And remember, the F distribution is also always right-tailed. It's actually always skewed to the right and right-tailed. Okay, so now we will not be spending time doing all of the individual computations. We will be given most of the computations already computed and need to either just make a decision or find the p-value from the F statistic and then make a decision. So let's look at number 5. A clinical psychologist wished to compare 3 methods for reducing hostility levels in university students. A certain test, the HLT, was used to measure the degree of hostility. A high score on the test indicated great hostility. 11 students obtaining high and nearly equal scores were used in the experiment. 4 were selected at random from the 11 and treated with method 1. 4 of the remaining 7 were selected at random and treated with method 2, and the remaining 3 were treated with method 3. All treatments were continued for a 1-semester period. Each student was given the HLT test at the end of the semester, with the results and the output shown below. Assume that the distribution for HLT scores for the 3 methods are normally distributed with equal population variance. So notice what they're trying to tell you here is we meet it, or I guess we shouldn't say we, meets the requirements for the F distribution. That's what that sentence is letting us know. Because notice the sample size is way too small. Okay, so we didn't have to do all the computations. This is software output that did the ANOVA testing for us, but we do have to know how to tell what is what here. So this information right here, that F ratio, that is your F statistic. This information right here where it says the F probability, that is your p-value. And then all of this information over here is just like we had before, degrees of freedom. This is going to be k minus 1. This is n minus k. Here's the sum of squares between groups. This is sum of squares within the group. This is the mean squares for each of them. This you get by dividing these two. And this is the F. This is the p-value for this particular F statistic. But what we need to be able to do, so the software has done all the computations for us, but we actually have to set up the test and report our conclusion to this test. So what is the appropriate hypothesis for assessing if there is a difference among the mean scores for the three methods? Well, the null hypothesis, first of all, we've got to figure out how many groups we have. And it looks like we've got 3 groups, one for each method. So my null hypothesis would be mu1 equals mu2 equals mu3. And the alternative hypothesis would be the population means are not all equal. That's the alternative. So that's what the test that we're doing. Again, the software did all of our computations for us. We just need to now interpret that software. So we're going to report our test statistic. Our test statistic is F equals 7.7150. We're going to report our p-value, which again from the software is 0.0136. So now I'm going to work on making my decisions. So 0.0136 compared to 0.05 is less than. When my p-value is less than, then my generic decision is to reject the null, and then I can make my conclusion in context, and that will be there is evidence that the mean HLT, so the score, the hostility, the mean HLT scores are not all the same for the 3 groups. And let's make sure we're a little bit more specific here. What we're saying is at least one is different. At least one of those scores is different from the others. Okay, so this is all we're really going to have to do for an ANOVA test. Now, just want to point out that, remember, in section 6.2, actually, I'm sorry, 6.4, we were doing hypothesis testing where we had to compare means. But remember, we were only comparing means for 2 groups, so we could do mu1 equals mu2. Now we're starting to look at means across 3, 4, 5, 6, many groups. That's why I can't use the methods that we used in section 6.4 where we're only comparing 2 means. we have to move to ANOVA when we want to compare many means.